Now let us see a very important topic today, trees and tree search. So what are trees? Trees, as you see in real life, they are something like this tree only, but they are considered upside down in data structures. Trees are essentially special type of grass only. So we can think of these trees in different ways, and we will arrive at similar definition when we talk about them. So a tree is an undirected connected graph without cycle. So tree is a graph which is connected, which is undirected. See, there will be no arrow, and without cycles. So there will be no cycles, means there will be no closed surface like this. A tree is also like a linked list where each node they have at most one previous pointer, which is exactly one node having none, and being allowed to have multiple next pointer. So it is also known to be a linked list where each node having at most one pointer and being allowed to have multiple next pointer. So this can also be node, this can be node, this can be a node, this can be a node, like this. So an undirected graph without cycles that may or may not be connected, they are known as forest. In a forest you can find many trees. So forest consists of one or more trees. That is why they are called as forest. How we can model in real world means the things or real problems which can be modeled to and from these trees. Family trees, that is either by going from one person to their parents, grandparents, and so on, and from one ancestor to their children, grandchildren, and so on. Also, they can be used in file system hierarchies, evolutionary tree among species, something like family trees. Also parsing human being languages or formulas or programming languages. Also finding shortest path in a graph, which is computed by BFS, as we have seen. A tree are very useful as the basis of many more complex data structures. Okay, so often offer much more trade-offs between these running times of different operations than their counterpart linear structures like arrays and linked lists. So when we are employing trees in the design of or analysis of data structure, we usually think of tree as directed, right? And there is a designated root node. So there will be a root node in a tree, and all edges point away from it. So we can have more nodes. They can be directed. This is how we think them in a data structure. So terminology, let us see the terminology of trees, and they are somewhat inconsistent mix of some botany and family trees. For example, if you have a node U which has a directed edge to V, then we say that U is a parent of V. So if you have U and here V, and this is an arrow, then we say that U is actually a parent of V or parent of V, and V is a child of U. And if U has a directed edge to node, say this was V, so let it be V1, V2, and likewise. These are siblings because they fall in the same level. And the root node, this is one node that does not have a parent. And since every other node can be reached from the root, which is U, we have all the edges. It's sufficient to have access to the root to find all other nodes, because this is from where we start. And nodes that can be reached from U, this particular point, with a path of length 1 or more, they are called as descendant of U. These are the descendant of U. And nodes that can reach V with a path length of 1 or more are called ancestors of V. these are ancestor of V. Please notice that we are talking about length 1, then only we can call it as descendant or ancestor. A leaf is actually a node without a children. So if you have a tree like this, right? So these are the nodes. This will not be these nodes or which doesn't have any leaves. They are known as we call them as leaf. A node with at least one child is called an internal node. For example, this is an internal node. This is a leaf. So when we talk about rooted tree, the degree of V refers to the number of edges out of a certain node. Degree is the number of edges which is out of a certain node. For example, this, it has a degree of 2. If a node has one edge from its parent and 2 to its children, that means it has one edge from its parent and 2 to its children, the degree is 2. Even though if we think of it as an undirected graph, we would call the degree actually 3, because 1, 2 and 3 if they are undirected. But for being directed, the degree of this node will be 2. And the subtree of a tree is a set of nodes and edges that are connected by themselves. So this part is a subtree of this whole tree. So most frequently used subtrees are those consisting of these nodes V and all its descendant, as I just showed you. And those are called subtree rooted at V, which is, if we know it to be U and this is to be V, so this is the subtree which is rooted at V. And it is frequently useful to think about levels of nodes. These are various levels, 1, 2, 3, these are various levels. So for any node V, the level V is the number of nodes in the path from the root V. So from any path, say this is root, the path means the level is the number of nodes in the path from the root. Means if this is what we are talking about, then this is 1 and 2. So from root, it has 2 levels, so it will be at third level. So the root itself is at level 1. Root is at 1. Then children are at level 2 and grandchildren at level 3 and so on. And some books you will also see that the level is known to be 0. Just because you want to implement it in computer science or computer language, for that you do something like this. So with this discussion, we have arrived at height of a tree, which is the largest level, because we have already known the level. The largest level of any of its node, we call it to be height. And more like other structures, we can use this recursion to say formally what a rooted tree is. For example, a root R by itself is a rooted tree, and depending upon how we think about calling an empty tree rooted, we could instead use this empty tree as our base case. Then we have T1, T2 up till Tk. These are rooted trees and rooted at U1, say U2 and UK. Then by adding a node R and directed edges, say R to U1, R to U2, R to UK, we obtain a rooted tree. So this recursive definition of a tree, this often aligns very naturally with our recursive algorithms for actual processing of data on trees, which we are going to see just now. So there are specific subclasses of rooted trees that are sometimes used in designing our data structures. Let us emphasize them somewhat. A tree is D-A-R-Y, okay, binary, say binary, tertiary, ternary, all these words come with suffix as ARY, array. So a tree is D-array if each node has exactly 0 or D. Means a binary tree will be either having 0 or 0 array or 2 array. It will have 0 node, 0 degree or 2 or 0 degree. And we also allow exception for one node to have one child. This D array tree is full if all leaves are at similar level. That is, adding one more node would require a new level to be formed. And what do we mean by complete? This is slightly less restrictive than being full, right? Full does not mean complete, and vice versa. And what about complete D array tree? D array tree, this has all its leaves at level h, or say h minus 1. And when we talk about complete trees, we also assume that there is a natural left to right order among the subtrees, and we will require that the leaves at level h are as far to the left as possible. That is, we will follow this left to right ordering. So many trees we will be using for implementing this data structure will be binary, but there will be some important exception with like 2, 3 trees in which each internal node has either degree as 2 or 3. So let us implement trees. We have seen about trees discussion. So trees, as we have suggested that they are special type of graphs only, so we could just use our general purpose graph implementation like adjacency matrix or adjacency list to implement them. Adjacency matrix, this matrices is the plural of matrix. They are quite not natural. Why? Because we seldom need to find out if two specific nodes are connected by an edge, but we frequently need to explore all children of a given node. And also, trees are extremely sparse. There is n-1 edges for n nodes. So this adjacency matrix could be extremely, waste of space. Then adjacency lists are more natural fit, but we can simplify them somewhat, since we are aware that each node has exactly one incoming edges, except for the roof, which has 0 incoming edge. So we don't need a whole list of incoming edges and can just store one pointer to the parent, which is actually null for the root. So this gives the structure of a node like this. Let us have a template, call it class T, class node. This will be one node. So we are talking about the structure of a node. We have a node. Actually, this node will contain a data. Then we'll have a node type parent, and we'll have a list of node type. This node type structure with a children. So depending on whether the order of the children matters or not, we may use this kind of children instead of the list. So set, we can also use set node. Exactly, I'm talking about this, but depending upon whether the order of the children matter or not, we will see this set, because in set and list, the order does matter, and in one of them it is not. So for a parse tree of an arithmetic expression, if you want to parse, the order of children evidently matters. For example, if you want 5 minus 2, the result will not be similar as 2 minus 5. But for some other, it may not matter. So many of our tree will be binary. So we don't need a list of children and can instead have a 2 pointer for the children. For example, this is the node, this is the data, and you have a parent, you have a left child and a right child. And in both cases, this one and this one, you should notice that we are storing pointers to other nodes rather than something just like this. So we are storing pointers to other nodes. These are actually pointers. Why this is important? Because we would like to generate just one object of each node and then just have points to it. If we don't do this, we store node themselves rather than the pointers, what will happen? We would be creating a new copy of node for each neighbor, and following around the structure would be quite hard. So what can be an alternative to this? The alternative to generating dynamic objects for nodes is to store all nodes in one array. Thereby, instead of storing pointers to the parent and children, we can just store their indices as integers. So this will give us a binary tree, which is actually idea of general trees itself. So it will be some node. This will be data. This will be parent, left child, right child. See, there is no pointer. So if the tree is complete binary tree, it will be more simple. So if we start numbering the nodes at 1, that is for the root node, then by just little experimentation, we find that the parent of node I is always node I by 2, and this is 2 children's, which will be 2i and 2i plus 1. But this formula looks quite different if we number the root with 0, but it's not that much difficult. It also generalizes to D array, or not binary means 2, but n array trees quite naturally. Now, how to traverse a tree? Now, this is an important concept. Traversing means visiting each node of the tree exactly once. So this is a very important idea and natural idea to do it by recursion or recursively, following the recursive definition of tree. So traversing a leaf is pretty easy. We just do whatever we want to do with it, like computation or printing. And traversing an internal node V involves visiting the node itself, then recursively visiting each of its subtree, which is rooted at its children u1, u2 up till uk, say k is greater than or equal to 1. So the main distinction is then the relative timing, that is whether we traverse the subtree first or do we visit the node V itself first. So this is exactly where we come up with post-order traversal and pre-order traversal. So if the tree is binary, it also makes sense to traverse at left subtree first, then visit the node and then the right subtree. And this order is known as in-order traversal. So we are going to illustrate these 3 traversals in this tree. This is a tree on which this traversal order are there. We would complete this T as a complete binary tree, even though technically this node 4 has only one child, which is actually violating our definition, but the concept is useful enough that I would like to not worry about this small detail right now. So the post-order traversal, we visit all the subtree first, then process the root, finally the root. So post-order, pre-order and in-order means post, pre and in. This is for node only. We are talking about node whenever we are going to traverse this. So the pseudocode will be something like this. We would consider a tree complete binary tree. We have seen that the node 4 is violating our situation, but the concept is useful. So this traversing will have a node which is R. For each child u of R, we traverse u and we process the data and output something, or computation is done. And as we apply it in our tree, we get this sequence. And in pre-order, we process the root first, then visit all the subtree. So the code will be something like this. We process data, for example, output something or computation, then each child of u of this traverse u. And in pre-order, the result will be something like this. Don't worry about this, I'll tell you how to get this. You concentrate upon how we are just changing the way we are doing traversing. In order, what we do, we visit all nodes to the left subtree, then the root, and then all the nodes of the right subtree. The code will be we traverse left child, then process the node, then the right child, and the result will be this. So this is in order traversal is most natural for binary trees. Okay, so let us start. Let me give you an idea. that if we want pre-order or post-order or in order. So let us start. I'll just give an example of one, and you'll understand that how we have achieved this. So let us assume that we are going for, say, this one, pre-order. Say pre-order. Okay, pre-order will be 0137849256. So this will be 0137 and 849256. 849256. 849256. So indeed we are talking about pre-order, and once I will tell you, you will be knowing how in order and post order will be done. So pre-order means first we'll go to 0, and since this is pre-order, we will take the node first, 0. Then we will go to the left one, and as soon as we encounter a node, we'll just place it 1. This is 1. Then we go to the left. Again we encounter the node, we write it 3. Then we again go to left. Again we have a node 7, which is the node, means root node of node tree. Then we go to the right. We find it 8, we write it 8. Then we go to the right of this tree, because we have already traversed 3. So for this particular tree, this left we have covered. Now we'll go to right. As we go to right, we see that 4 is the node, root node. We write 4 here, and then we go to the left. We see 9. We write 9. Then this part is over. This already we have taken care. Then we go to the right, this subtree. Then as soon as we encounter 2, we write 2, because in this kind of pre-order we check for the node, the root node. Then we go to the left, we take 5, and then we go to the right, we take 6. So this is an example of one of our traversal. Hope you will be able to do the in order and this post order also. So if node has more than 2 children, then what? We would have to make decision what is the right point to process its own data. So if the node has d children, d minus 1 pieces of data, then it makes sense to alternate between the children and pieces of data, and we will see them in 2-3 trees later on. Now important aspect is how to search tree, because we have seen about trees and traversal. Now searching trees. So the key property that makes this binary tree a search tree is that following things hold for every node, any node v. Let k be the key in node v, and t1 and t2 are the left and right subtree of v. If v is there, then we say that t1 is the left subtree, t2 is the right subtree. So all keys in t1, these t1 are less than or equal to this k, and all keys at t2 are greater than or equal to k. K is this number. For example, let us illustrate. See, this is 5. All nodes left, that is t1, are less than 5, that is 4 and 2 are less than 5. And all these nodes are greater than your 5. And in this subtree, see, though all these numbers are greater than 5, in 8 also, at this node also, it should follow, means 7 is less than 8 and 12 is greater than 8. So this is this property is satisfied everywhere. So exception is 12. Why? It is the left subtree of the node labeled as 10, which violates, because at 10, 12 is greater than this 10, which is violating the condition. Which is violating that all keys in the left subtree of a given tree are smaller than the key in the node itself. So let's figure out how to search for a value of tree. Suppose that we are looking for some key which is k in a tree rooted at v. So there will be 3 cases. If the tree is null or empty tree and k is not there, we report. That is some exception we will throw. If indeed data is there, the key is at the root node, then we can just return the root node in some form, that is we at k, that means the root node is where the value is found. If k is less than the value or k is greater than the key, then we search tree or guarantees that k is either to the left of v and not in the tree at all. So we recursively search for left subtree, and similarly for the right subtree. And you have to notice the similarity between this search and the binary search. We repeatedly query a middle value. So once if we want to find say 4, then we know that it is to the left half or left subtree. So we will drop all these values, we will not even check. So this is somewhat similar to our binary search. So we recurse in one subpart. It is quite easy from a search tree to obtain a sorted array of all entries. Just perform an in-order traversal of the tree. So if you perform in order, you will have a sorted number or sorted order. So the advantage of such tree over these sorted arrays is that we can rearrange tree just a little bit at a time, rather than having to shift huge numbers of items around for every insertion. So search in a search tree is fast as binary search. We know binary search is very fast. We'll also see insertion and removals also. So we have asserted that search is in a search tree is quite fast. We have just seen, and we also analyze that search algorithm, which is what we have showed here, that each step takes constant time and increases the level as we are searching by one. So the time to search for an item is theta height of t, and because whenever the height is small, this order of log n search tree will perform great. But as the height grows, then what? Consider this example. This is example. These are some ideal examples, but what about this? This tree doesn't look like a tree, as it's basically a linked list, but it is a tree. So its height is n, the number of elements, and so a search would be really slow. So in order to keep height small, ideally our tree should be close balanced. For any node, the difference in height of its subtree should not be too big. So the tree will look almost like a complete binary tree, and it is easy to see that a complete binary tree has always a height of order of log n. So how do we make sure the tree remains somewhat balanced? And we are going to see about this. This is actually a degenerate search tree, and here a search for the number 1 or any number would take a linear time in the number of elements, which is actually a linear search only. So hope you got the idea about tree traversing and this traversal and various other aspects which we have seen, and we'll be talking about various tree soon. Thank you so much.